Welcome back, ladies and gentlemen. So, we have been spending our time learning ionic and covalent bonding. We've learned about how ions, of course, are positively or negatively charged atoms that then come together because of electric attraction, and how covalent bonds are about the sharing of electrons between nonmetals. And now we're ready to begin something a little different. You see, in grade 9, you learned the alphabet of chemistry. You learned the periodic table. And now at the start of grade 10, you've started to learn the words of chemistry. You've learned how to take those letters and start to stick them together. It's time for you to start learning some sentences. Yeah, because this analogy can go pretty far. So, what's an example here? Well, for our purposes, we're going to start ourselves off with our simplest example, the one that we are known and we know very well because we've done it so many times. So, we're going to start off by saying hydrogen gas and oxygen gas are combined to produce water. This is a sentence that you probably know. You know all about water. You've used it a lot. You've seen it for many years now. But here is a sentence to describe how to make water using hydrogen gas and oxygen gas. And we combine it to make the water. The notes talk about how this is the transformation of atoms and into making compounds. Now, there's a bunch of different things to see here. We're making the compound of water. We would call this a product. And we made it from some starting materials, the hydrogen gas and the oxygen gas. Those are called reactants, or reagents if you use a slightly more old-fashioned way to say it and want to sound like a wizard. Now, writing big sentences like that's a lot of work, and we don't always do that because work is annoying. So instead, what we're going to do is we're going to use some chemical formulas. And you know this. You hopefully remember the fact that hydrogen gas is a diatomic, so it's going to be H2. And I'm going to combine it with oxygen, and in this case means add. And I'm going to produce water. This is known as a chemical equation. And all it is the symbol representation of this sentence up above. Much like how a math equation can be written out by hand and put in words, I can write words of this sentence of what we're doing into a chemical equation. Now, there are quite a few different little things here that we need to understand, right? I mean, heck, I haven't even drawn all of them. There's a couple more, too, because it did say these. Let's see what they are. First one, we've got this plus sign here. What's the plus sign? Well, the plus sign basically just means combines or reacts with or adds. Basically, the plus sign is the same as a plus sign in math, because again, as we've discussed, most chemists are nerds. What about this arrow? Well, the arrow is produces or reacts with or becomes. Basically, it's the chemistry equivalent of the equal sign. The difference is that the equal sign means that the two sides are the same. In this case, we're saying that the left side turns into the right side, which is why the arrow only goes one way. What happens if I could go both ways? Well, then I'd have to put two arrows. But we don't deal with that in grade 10, so let's just get rid of that. Anyone skipping through the video, they're not going to see it. They're not going to know. It's a secret just for you and I and whoever watched all the way. Now, there's also these symbols under here in brackets. Those ones aren't as hard as it looks. Important fact, they're actually quite obvious. The G here means gas. The L over here, written handwritten to make sure that it doesn't get confused with a 1 or something, is liquid. Now, not shown here, of course, are two more. There's going to be S for solid, and AQ for... what could AQ be? AQ is a weird one. It means aqueous, which it's Latin, because again, those Romans and their Latin coming in everywhere. Aqueous means dissolved in water. It's just a fancy way to say dissolves in water. Why is that important? Because it turns out a lot of chemistry happens in solution. We pour things into water in order to mix them up and spread them around and do stuff with them. So there you go. This is a chemical equation. The information that was up here is now down in here, and it's written in a lot simpler form. I mean, yeah, okay, I've got all these definitions kicking around all of this, which is making it more cluttered, but by itself, the core is just this, and this, and this mean the same thing. But we're not done yet. No, not yet. You see, there's a problem here. I don't know if you've spotted it, because it's subtle. But basically, this isn't going to work. What do I mean? Well, let me try drawing this so you can see it. I'm going to have myself some hydrogen gas, right? And it's covalent, so it's going to share. So here's some good old hydrogen gas sharing away. And then I'm going to have some oxygen gas. Now, oxygen, of course, has 6 valence electrons. I'm going to draw them a particular way to make my point easier. And these guys are covalently sharing. Now, that's step 1. Step 2 of our chemical reaction. I combine these two. I add them together. I slam them into each other, and I turn them into something else. But I don't go immediately from H's and O's to H2O. No. What happens? I'm going to go into this. As soon as the hydrogen gets close, the oxygen, which remember only pairs up with another oxygen if it has no choice, the oxygen is like, whoa, there's a hydrogen here. You get out of here, loser. I want to team up with the hydrogen. So they do. And then since there's an empty hydrogen there, well, the other oxygen is like, well, I don't have a friend. I'm going to get a friend. And now I've got this. And this is not water. This is good old H2O2. Hydrogen peroxide. That's the kind of thing that if you decided to have a nice, cool, refreshing glass of hydrogen peroxide, yeah, you wouldn't enjoy that. That'd be lethal, very lethal. So how in the world are we going to go from there to H2O? We're missing something here, right? Like, we need another hydrogen. You'd think, right, that maybe this guy could have attached over here. But no, of course, as soon as I break this connection, the hydrogen and the oxygen are immediately going to connect together. But then the same thing's going to happen here, right? They're not going to, oh, no, sorry, I'm going to wait for the other guy. No, he's busy. He's immediately going to connect. So what do? We bring another hydrogen. We bring that hydrogen in on the other side because there's more than just 2 molecules in this thing. And these guys over here, of course, are sharing just like the other ones, but they come in and the same thing happens again. This guy here goes, hey, there's another hydrogen. I don't need you, loser. Get out. These guys pair up. Then these guys pair up. And what do we get in the end? We get something that looks like this. when you look at that, we made water. But we didn't just make one water, did we? We made two waters. And those two waters aren't connected. Do we remember how that works? Can we put that together? Why, if they're not connected, but there's two of them, I put a coefficient in front. I made two waters with, let's see, one oxygen, but two hydrogens. This is known as a balanced chemical equation, and it works on the fundamental idea that you can't create or destroy matter. Everything that you put in is what you get out. In order for me to make the two waters, I need to put in two hydrogens. And the reason I need to do that is because, as we saw when we went through these steps, these two hydrogen do not just split apart and both attach to the same guy, because this other oxygen muscles in, gets in the way. So they need a second hydrogen to finish the job. Otherwise, instead of making some sweet, sweet H2O, we make some super deadly H2O2. This whole idea is the basis of making sentences in chemistry, of writing out balanced equations. This is how we create new things from starting materials. Now, you're not expected to draw all these out all the time. I did that to try and showcase. But you are expected to be able to balance a chemical equation. And the golden rule, everything you put in has to equal everything that comes out. There has to be the same number of pieces on both sides. Right? If we look over here, there are two oxygens. Well, there's one oxygen here, but there are two of these guys, right? 1, 2. So there are two oxygens. There's two hydrogens times two, so there's a total of 4 hydrogens on one side. And if I look here, I've got 4 hydrogens. Everything that went in is what comes out. That's so important. I'm going to write it on the board. Everything that comes in must come out. So everything we're about to do is built on this idea. Let's try some examples. Okay? Take a look. The key things to know, right? We can't change these subscripts. It's not allowed, because the subscripts tell us stuff is connected. If I were to change these subscripts, that means that I'm making a new chemical. I'm not making water anymore. I have multiple waters, and they are not connected. They're both the same, which is why the 2 goes in front. So, let's try one. We'll erase this, get a little bit of space. Not every one of them is going to be as simple as water, of course. So the example we've got here in the notes, we've got HCl plus MgBr2 is going to make MgCl2 plus, is it HBr. Okay, so we need to make sure that everything that goes in comes out. That is our goal every time. Now, there are a few different ways to do this. I'm going to show you the way that I'm going to recommend, but you can do it however you want. And once you do enough of these, you're going to kind of find that you can sort of do a lot of this in your head, because you'll get used to it. You'll figure out what's going on. So the first step I want you guys to do is I want you guys to list off an inventory of all of the elements, a chemical inventory. So for example, H, Cl, Mg, Br. You'll notice I've written them right down the middle here underneath the arrow. Now the purpose of this is to make sure that I have them lined up on either side. This is going to be very useful for us when we do our next step, which is to list down how many there are. there's one of these, and on this side, there's one of those. On this side, I have one chlorine, but on this side, I have two chlorines. See, I can immediately compare the two guys. It's not like I'm checking them in two different places. I've got one magnesium, but I've got two bromine and one bromine. Now, our golden rule, everything that goes in has to come out. I've got two chlorines, one chlorine here and two there. I've got two of these and one of those. These two guys already check out. They're good, but these two aren't. Now, in order to make changes here, I cannot change the parts in black ink. The chemical equations must stay the same because those use the rules of ionic bonding or covalent bonding. Those rules we already learned and they're already true and we can't change them. Right? I can't just change the spelling of the word because I want to. Oh, I need to put a few more E's in this paragraph? Well, I'll just throw some E's in the back of hand of hello for no reason. Can't do that. But I am allowed to change the number of each word. I can't put extra E's into a word, but I can put another word that has E's in it, kind of thing. So here's how we do it. There's one here and there's two there. I'm going to multiply 1 by 2 because that'll make 2. Now I'm doing math, sort of written it backwards from the center point, which can throw a few people. This 2, I'm doing it by putting a 2 up here. Again, I'm not allowed to put the 2 down here. That's against the rules. I can't change the structure of the chemical formula, but I can say I got 2 of these dudes, just like I had 2 hydrogens in the previous example. Okay, now there's a bit of a problem because that 2 that I just did is going to also change the hydrogen by 2 because these guys are connected. They come as a package, right? I'm basically saying I'm going to have 2 of these guys. So there's 2 hydrogens. It's a problem, but it's not a problem for long because watch. Next, I'm going to check bromine. Well, I got 2 here. I've only got 1 there. So I'm going to do exactly the same thing. Times it by 2 gives me a 2. So doing it in red, I come up here. I find where the bromine is. I put a 2 in front. I multiply the hydrogen by 2. Take a look at that. If I compare every single line, I've got 2 and 2. This line checks out. I got 2 and 2. Checks out. 1 and 1. We're good. 2 and 2. We're good. Everything that went in came out. This is now a balanced equation. What we're seeing here is the ability to organize things. All of this information down here, this was just our work. I can erase all of this, and now I get my final answer right there at the top of the page. That's it. That is how you balance chemical equations. Now, okay, sometimes it's a little bit trickier, but one of the nice things about this is that you always have the answer key with you because everything that goes in must come out, whatever that is. So I can always check. I can look at it and go, oh, let's see, I got 2 hydrogens there. I got 2 hydrogens there. 1 magnesium, 1 magnesium. 2 chlorines, 2 chlorines. 2 bromines, 2 bromines. I can check it after I'm done. Let's try another one. Next one on our list. Al2 S3 plus CaCl2 goes to make AlCl3 plus CaS. Okay, step 1, inventory of the elements. We have aluminum, sulfur, calcium, and chlorine. Okay, now we need the numbers of each. I've got 2 aluminum on the left and 1 aluminum on the right. I've got 3 sulfur on the left and 1 sulfur on the right. I've got 1 calcium on the left and 1 calcium on the right. Finally, I have one that isn't crazy. Chlorine. I've got 2 chlorine on the left and I've got 3 chlorine on the right. So we have a whole bunch of differences here. Only one of them is even remotely the same. Now, black goes down. Switching over, we're going to go with blue. I need to start making some changes, but I can't change the black ink. I can't change the way that the molecules are written, the compounds are written. I can't change the subscripts. Those have to stay the same. But I can change the coefficients. So let's go with the aluminum. I'm going to multiply by 2. That means I'm going to put a 2 in front, which means I'm also going to affect the chlorine. It's also times 2, making 6. Okay, now that fixed the aluminum, but it broke the chlorine. That's annoying. Let's try fixing the chlorine now. I've got to multiply this side by 3 in order to make 6. So I find my chlorine, I'm going to put a 3 in front. If I do that, I'm going to get, of course, times 3 on the calcium. Ugh, now the calcium's broken. All right, red goes away. I'm using different colors to try and make sure you can see which ones are connected together. Let's fix up the calcium. I'm going to multiply this side by 3. So that means a 3 goes in front, and now that's going to affect the sulfur. All right. Hey, we lucked out. I don't have to do anything to fix the sulfur because the sulfur is already good. So, there it is. We've got 1 of these, 3 of these, 2 of these, and 3 of these. Remember, everything down here is just our attempt at bookkeeping to keep track of all of the different materials. This part up here, this is the actual answer to the question. And of course, the key is that everything that goes in must come out. Okay, maybe we should do another example. Just another one to make sure we get the hang of this, okay? And let's ramp it up a bit. We'll make this one incredibly difficult, so impossibly hard that it's unlikely that you will get it right. Are you ready for this one? Probably not, but we'll see what you can do. C plus O2 goes to make CO2. All right, I know, there's not a lot there, but obviously this is still very difficult. Not really. Inventory, we've got C's and we've got O's. Okay, so far so good. I've got 1 carbon on the left, 1 carbon on the right. I've got 2 oxygen on the left, I've got 2 oxygen on the right. Oh, we're done. That's it. I may have oversold it a bit. There isn't that much to do here. At the bottom of the page with examples, you will see something very unusual. They are words, sentences. It's an extra step to things. I'll show you an example now, but I don't expect you to do this right away. If you take a look in the next couple pages, most of the practice involves formulas. And we're going to be doing that for a long time before we come back to this bottom 2 examples. But I'm going to show them to you now. If you don't want to see these right now, you can always pause the video and work through it at another time. But I'm going to do it now just to make sure that we've got something to work with. The example says that solid aluminum which I might have even spelt right. Nope. I made it aluminium. Apparently I'm even more British than previously expected. Aluminum combines with chlorine to produce solid aluminum chloride. So this is a sentence to describe chemistry. In order for us to be able to write a balanced equation, the first thing we have to do is write an equation. Now we did that already earlier in the video when we talked about water. We made hydrogen gas plus oxygen gas makes water. Same thing here. It's just basically we're adding one more step before you can actually get to solving the question. So Solid aluminum. That's easy. It's just aluminum. Plus chlorine gas. We know what that is, Cl2, because it's one of the diatomics, right? It's one of the ones in the upper corner quadrant, that L shape on the periodic table. Is going to produce, that's the arrow, aluminum chloride. Now we have to write this properly. Aluminum and chlorine. Aluminum, if we check, is in the boron family. It's 3 plus. Chlorine is in the halogens. That's 1 minus. I have to make sure the two sides are balanced. So that means that since this side is 3 plus, this side has to be 3 minus. To do that, I need to have 3 times as many chlorines because each one of them is only worth 1. So this is going to be AlCl3. Okay, now that we have our chemical equation, now we can do all the stuff we were just doing. I mentioned earlier in the course that this is a course that builds on itself. You need to know the alphabet before you can do words. You need to know words before you can do sentences. You need to know sentences before you can do paragraphs. We're not getting there yet. That's grade 11 and 12. But if you don't know how to do words or sentences, you're going to have a hard time, right? If you don't know the alphabet, you're already going to have a hard time doing any kind of writing. Okay, chemical inventory time. Aluminum, chlorine. I have 1 on this side, 2 on that side. I have 1 on this side, 3 on that side. Now remember, this is a 2 because it's a diatomic gas. This is not a 2 because that's not what the ionic bonding says we should get. The black marker goes away now. This part is all fixed. Now we have to work with what we have. This is a 2, this is a 3. This is a common problem you're going to run into. Because they're 2s and 3s, I can't turn one into the other because I can't multiply by a fraction or a decimal. That's okay. 2 and 3, let's just make them 6. Times this side by 2 makes 6. That's also going to times this guy by 2. That's a 2 in front. Then I'm going to come over here, and I want to make this guy also 6. So I'm going to times him by 3 to make 6. Put a 3 in front. Now we just have to fix up the aluminum. Times 2 is equal to 2. And there we go. We are now done. The actual balancing of this one was easier than the one we just did. But there was the extra step that we needed to work out what the formula looked like before we could solve it. Now, that about sums it up. Those show all different examples of balancing. There could be some unusual things here and there that you might run into. Some general advice. Try to turn, if you see odd and even numbers like this, like you got for chlorine, try to turn those guys into the same number, an even number of some form. That's going to happen an awful lot, especially with oxygen, because oxygen has often got an O2 somewhere, but there might be an odd number of oxygens on the other side. Another piece of advice, if on one side of the equation, usually the reactants, you've got something very, very complicated, like it's got lots and lots and lots of pieces, touch it last. Leave it alone for as long as possible. Because the moment you change even a little bit, it just cascades through everything and it makes a mess. So leave that alone. And of course, a big one, everything that goes in must come out. So you can check your own work. You don't even need my answer key at this point. Now, that said, you have it, and I recommend using it, but you don't need it. Okay, that's about it. I will see you guys next time.